In this video and the next one, we are going to derive some of the more profound results that we're going to touch on in this course. You won't need any of these results to solve problems that you might encounter, but hopefully they will help you to understand physics on a deeper level. So we've already introduced the generalized force, which is just the partial derivative of the Lagrangian with respect to a generalized coordinate. And we also have a generalized momentum, which is the derivative of the Lagrangian with respect to the corresponding generalized velocity. So this, of course, means that when we write down the Lagrange equations, that really corresponds to Newton's second law, right? Or some version of it. And if we're working in Cartesian coordinates, I should use consistent notation here. If we use working Cartesian coordinates, then of course this generalized force is the actual force and generalized momentum is the actual momentum. So this we already know, but we do notice something here, which is kind of interesting from this. That, of course, if the generalized force is 0, then the momentum doesn't change over time. But generalized force is 0 if the Lagrangian doesn't depend explicitly on the corresponding generalized coordinate, right? So if the Lagrangian is independent of q sub I, then p sub I is constant. In other words, it's conserved. We interrupt this lecture for an important vocabulary announcement. Basically, I forgot to add this to the lecture, and I don't feel like re-recording it, so we're doing it this way instead. So what I wanted to say here is that if a Lagrangian does not depend explicitly on a generalized coordinate, just like what we've seen, let's say Q1, so the Lagrangian can be then written in this fashion. It will depend on Q2 and maybe other generalized coordinates as well. It will depend on Q1 dot, but not on Q1. And this means then that P1 dot is 0, or that P1 is a constant. The generalized momentum corresponding to this generalized coordinate is constant. If that's the case, then this generalized coordinate is said to be ignorable. Okay, so once again, generalized coordinates that do not appear explicitly in the Lagrangian are known as ignorable coordinates. That's a reasonable description. It doesn't mean we can completely ignore them, as we will see, but that's what they are called. It's the better name of 2. Sometimes they're known as cyclical, and that's kind of misleading. But we're going to refer to generalized coordinates that don't appear explicitly in the Lagrangian as ignorable. We now return to your regularly scheduled lecture. So there appears to be a link between translational invariance, that is, the Lagrangian doesn't depend on the value of a particular coordinate, and momentum conservation. So to be explicit, let's think of, for instance, a particle in the gravitational field. So in that case, the Lagrangian is just 1/2 m times x dot squared plus y dot squared plus z dot squared, and then we have to add in also minus the potential. Okay, that's what the Lagrangian is. We have that the force in the x direction, dl dx, equals 0, and the force in the y direction is also equal to 0. So that means, of course, that both momentum in the x direction and the y direction, both those momenta are 0. And that comes from the fact directly that the Lagrangian doesn't make reference to the variables x and y, only to the corresponding velocities. So maybe there's something more profound there. So let's see if we can't derive something interesting starting from this train of thought. So let's say that we have a system of particles. So they're over here. And they're all interacting with one another through some potential. And they have various positions which might vary in time. You know, R1, R2, R3, R4, etc. And what we're going to do now is we're going to translate this isolated system. So that's important, actually. It's an isolated system of particles. We're going to translate a small distance, dr. So all these guys translate some distance, dr. Okay? So let's see what the consequences of that might be. Well, if you look at the potential energy, at points r1 plus dr1 plus dr, r2 plus dr, etc., is the same as the potential at the original position, because there are no external forces. So U depends only on the differences between two positions of particles, like r sub I minus r sub j. So if I translate all the particles by some distance, then nothing happens. And similarly for the kinetic energy also doesn't change, because if I just take the system and move it by some distance, you know, essentially that didn't change the velocities. All I did was just move what's happening over to a different location. So same thing for kinetic energy. So what does this mean? Well, it means that if I calculate the change in the Lagrangian, dl, there's going to be the Lagrangian now that depends on r1 plus dr, r2 plus dr, etc., and also the velocities. minus the Lagrangian at the original position. That's going to be equal to 0. Then we can also apply the chain rule. And the chain rule says that the L here is the R scalar, now the gradient of the Lagrangian with respect to the first particle plus the R times the gradient of the Lagrangian with respect to the second particle, etc. Right? Now, to make things a little simpler, I'm just going to say that dr is just in the x direction. Right, so it's the x equals x hat. So that means that this simplifies a little bit. The L just becomes the x times partial the L, the x1, plus the x times partial the L, the x2, etc. And the L, of course, still equals 0. We can write this now as a sum. The x alpha partial the L over partial the x alpha equals 0. Since this is true for any dx, including the x's that are not equal to 0, this gives us that the sum of all these derivatives is 0. And that follows directly from this, right? All that we did was we translated the system by some distance, and since the Lagrangian didn't change, we got this result. Okay, now we have the Lagrange equations. Which says that, well, the generalized force equals the time derivative of the generalized momentum, as we know. And what we've done here is we've summed up all the generalized forces in the x direction, and we could have done the same thing in the y and the z direction. So if we do that and we find that they're all 0, we can use Lagrange equations here to say that the sum of the momenta of all the particles, from 1 to n or however many we have, that's 0, particularly in the x direction. We should remember we're still working in the x direction. So that's a 0, and we can now change the order of the derivation here and the summation. And that is now the total momentum in the x direction. So that means that ddt of px, the total momentum, is 0. And that, of course, gives us that p of x equals a constant. And the same thing works in x and y. Or, I mean, in y and z, of course. Because it works both in x, y, and z, the result is that the total momentum, p, is conserved. Well, we already know that. But it is conserved because the laws of physics are invariant under translation through space. So we have momentum conservation because the laws of physics are the same everywhere in the universe. So if you ever wondered why momentum is conserved, this is, at the deepest level, the reason for that. So this is one conservation law, conservation of momentum, due to translation through space, due to translation invariant through space. We have other conservation laws of energy and angular momentum, and in the next video we're going to deal with them as well.